All right, so start beginners night about networking, just basics networking, Linux networking, all that stuff. So just like last time, it's pretty informal. If you have questions, just shout them out. Probably a lot of them, that's what the point of these talks are. So if you want me to explain anything that I didn't cover too well, go over something again, just ask. All right, so basics networking is this thing called the OSI model. So basically it's a 7-layer breakdown of how information gets from one computer client to another, the server, starting with the physical layer all the way up to the application layer. So our bottom we got physical, which is just like the Ethernet cable or the Wi-Fi, something like that. Data link, that's the MAC address, which we'll talk about soon. Network, got like IP addresses. Transporters, basically two. We got a TCP, UDP. Session presentation are kind of intertwined with application a little bit. A good mnemonic to remember the order from bottom to top is please do not throw sausage pizza away. There is another one from top to bottom, but it's not memorable, and I know this because I forgot it. Another diagram, it's more simplified, it's called a TCPIP. This combines presentation, session, and application to one because they're still not really too separated. There's kind of some overlap. Data link and physical combined as well. Network's name becomes internet because it does. So there's two models. Important to remember, these are both theoretical. So if you ever see a protocol that doesn't really fit nicely into one of these, or it overlaps, or it seems like it should be on its own layer, well, that's why. It's just a theory. But it's a good place to get started. So we'll start with hardware. You got a MAC address, which is not related to Apple. It stands for Media Access Control. Basically what it is, it's a unique identifier that is assigned to everything on a network. There are 2 to the 48th possible addresses, so every device should have a unique one, no overlap there. And it's used on the local network to differentiate between machines. It's used by a switch so that when different computers on the same network, they know which traffic is theirs. So you got this thingy over here, basically just reads all traffic on network, and then it pulls in what matches the local IP or local MAC address, so it knows which traffic to read. The first 6, well, MAC address looks like these 12 hex characters in a row. The first 6 are dependent on the vendor, and then the last 6 are just a serial number. So it looks kind of random, but there is some order to it. And important thing to remember is that MAC addresses can be easily changed, just as like any other setting on a computer. There's no real issue with that, it's just how they're set up, so they shouldn't be used for like authentication or anything like that, but it's a good way to just get network traffic organized. Then up to layer 3, you got the Internet Protocol address or IP address. Probably familiar with IPv4, it looks like this. You got 4 sets of 8 bits to print out an address for your machine. Used to communicate across the internet. This is done by routing. IP address on a local network has to be unique so that they can be differentiated. If you have 2 machines with the same local IP address, the traffic will get all gargled and confused. Private ranges of IPs can be used repeatedly. We'll go into more detail what a private range looks like. On a local network or on your home network, it's probably 192.168.x.x. And the network adapter can have more than one IP address if needed. So there's 2 basic types of internet protocols. You got IPv4, which you're probably more familiar with, and then the newer one called IPv6, which is longer and more complicated. This because IPv4 is only about 4 billion or so unique combinations, which we've been running out of that, or been in the state of running out for what seems like 10 or so years. So that's why IPv6 was created, so that we wouldn't run out. But the integration of IPv6 and being the standard has been kind of delayed because we've really not ran out yet. But that's supposed to be coming at some point. It's halfway implemented. It's kind of weird how it is right now, but it's there. Any questions so far? Yeah?
What would happen if you ran out of IP addresses with IPv4?
Newer devices wouldn't just be assigned one, I guess, because first bits are assigned by the ISP and they just run out, so no one will really get an address at some point.
So what would that mean for the device? Like, would you not be able to connect to a network, basically?
Oh, you wouldn't be able to set up more networks, I guess, is the best way of putting it. Any others? Yeah.
You said that 2 devices with the same IP address, the information can send to those devices that are garbled, which is
like if they have the same in the local one, you really can't differentiate the traffic since it's supposed to send to a one by its IP address, but if there's two in the same network, it doesn't really know which one to send it to.
So it's like half and half, technically, both devices are unpredictable.
Other questions? Okay. So talk about Netmasks. Netmask is a value that basically describes how many local machines can be on a network. So four types of subnets here. We got /32, /24, /16, /8. First one, /32, Netmask could be 255.255.255.255. Not useful. You only get one host. Yeah, that's not very used ever that I know of. More commonly, you'll see 255.255.255.0. It's called a /24 subnet. Here you can have 254 unique hosts on a network. This is what you'd see on like a home network usually, or a small business. And then there's last two, 255.255.000, that's a sub-16, and 255.000, sub-8. Those is what you'd see on like a big business, school, college campus, something like that. So some examples. First one is for IA states. This is a /8 subnet. So their local IP ranges can go from 10.001 to 10.255.255.254. This allows for about 16 million unique hosts, which is enough for everybody on campus. There are multiple devices, stuff like that, all the computer labs. Another ISU-owned one is 129.186.0.1 to 129.186.255.254. This is a /16 subnet that is also used. The name's a bit confusing because 129.186 is very close to the one you'd see on like a home network, which is 192.168. Don't get that confused though. Two different things. All right, so I talked about public versus private IPs before. Private IPs, there's been a few groups of allocated IPs that are reserved for private ranges so that your private IP address doesn't reflect like an actual website, just for convenience and simplicity. So the three ranges are 10.001 to 10.255.255.254. That was the one I showed you in the last example. Another one is 172.16.01 to 172.31.255.254, depending on the size of the network. And then the last one you're probably most familiar with is 192.168.01 to 192.168.255.254. That's what I typically see in a home network. Your router is probably on 192.168.01 or 192.168.11. All right, so routing. So to get from one machine to another, you have to go through what's called a routing table. So if you're PC 0 and you want to get over to, say, PC 1, you got to follow a certain routing path. First, you would go to the switch, then up to the router. The router would then connect you to router 1, back down to switch 1 to PC 1. So your computer has to know in some way how to get from PC 0 to PC 1. It has to know the route. This is accomplished through routing tables. So say you're PC 0, you look at it and you want to get to 172.1.8.0.0, which is over here in router 1. So you'd look over, it would look at its network and say it's not here, so you need to go up to router 0. And that's what's stored in the routing tables. It stores the next hop. So that's all it knows. And then same for 172.20, that is over here. Again, you have to go up to the router, so the next hop is still router 0. And then 172.16, that's on a local network, so it doesn't have to go to the router, it's just on link. So after it goes from PC 0 to router 0 in the first two examples, it reads a routing table for router 0. So again, say you're trying to get to 172.1.8, router 0 has to go over to router 1. That's how it's connected. So it'd hop over to router 1, go through that routing table, and cycle continue. Same goes for 172.20, it's over here. They're connected through router 1, same issue. And then 172.16 and 172.17, those are within the range of router 0, so it doesn't have to hop anymore, so it's on link. Okay, NAT. So NAT is what allows basically multiple computers to be on the same network and share an IP address and not have connection confusion. So say you have like two computers that are on the same network and they're both accessing Google at the same time. So you have two sessions coming from the same IP address, but they need to go to different computers. And Google can't tell them apart. They're from the same IP address, does no difference. So that's where NAT comes in handy. So you have device 1 and 2, they're behind the NAT router. And what the NAT router does is it will translate both of their local sessions to what's going on the outside internet. and it will keep track of these two individual sessions to make sure they don't get separated, because Google does no difference, but your NAT router will, and it can send traffic to both machines as needed, even though it's sharing the same IP address. So, a few common protocols based on the OSI model. So on the back of the network layer, talk about IPv4, IPv6. There's also IP or ICMP, which is used for error messaging and stuff like that. It's technically under layer 3, but some people say it doesn't belong there. It's its own layer, it should be somewhere else, but it doesn't really matter. Again, it's a theoretical model, so nothing to worry about. Transport layer, layer 4, there's basically just two models, or two protocols, and they're called TCP and UDP. UDP is what you'd see on like a streaming service or when you're on FaceTime with somebody. Basically, the server just sends out the data and hopes you get it. So if you drop it, then you drop it. And the reason this is used on streaming services is if you do drop a packet, you don't want to just buffer every like 8 seconds for every single drop packet you have. You just want to have it get a little bit pixelated and then move on. TCP is the opposite. You want to make sure you get every packet, and it'll pause and wait for them all if needed to. That's the standard basically, and then UDP is just used whenever that would be useful for like, if you're like in YouTube streaming, Twitch, or gaming, something like that, that's when you use UDP. TCP, basically everything else. Then the top, we got the application layer. You got DNS, good quote from former member Matt Gerst. It's like the address book of the internet, so when you want to go to Google, you don't type in 8888 to the address bar, you type in google.com. So, and then DNS is what resolves that address to an IP, so your network actually knows where to go, because it doesn't really know google.com means. It translates to 8888, gets the IP, and then it goes forward from there. HTTP, you know, that's what your browser uses to load websites. FTP, file transfer protocol, transfer step between different networks. SSH, secure shell, that's if you're on a computer and you want to get into a shell of another one over the internet, you use SSH. SMTP is used for email. IRC, Internet Relay Chat, old chat room service, not really used as much anymore because you have alternatives like Slack, Skype, Discord, but there's still a few people that like IRC, so it's still living. Questions over any of that? Okay. So moving into Linux networking stuff. So the form for these slides is just going to be the command on the left and then different ways that it can be used, different switches on the right. First one we have is ifconfig. This is used to display information about how your network is set up on your local device. So basically just type ifconfig, it'll print out the information, it'll print out like your DNS, your IP address, IPv6 address, default gateway, some Netmasks, stuff like that. Plenty of switches you can do to modify it as well. Next up is IF up, IF down. It looks like if up, if down, but you're not asking if the service is up. You're saying go up, go down. So basically the main use for this one is if you want to modify your network setup in any way, you would do IF down to bring it down, make your modifications, and then do IF up to bring it back up. Not too much to this one, just bring it down, bring it up. All right, route. Route is, this prints the routing table like we talked about before to see what hops your PC is making. It can be used if you want to set up static routes between different networks. A couple switches too. Netcat. So Netcat is used to read and write data between networks. Basically what you do is you just set up a connection on this port, say like netcat-p, and then you're listening on port P, then someone, if they want to write to you, they'd use a command nc-l or nc-w to write to that port while you're listening on it. Just a quick way to transfer data. Dig, DNS Lookup, and Host. These have a lot of switches, but they used to perform DNS queries. There's probably about 8 different ways for each one that you can use, so check the man pages on these. Best way to learn how they work is just try them out on the same website, just like IASG.edu. Go through them all 3. A lot of switches and stuff for this ones. All right, ping and traceroute. Familiar with these. Ping, good way to see if you have a connection between a server or not. Basically what it does is it will type ping and then an IP address or website, and it will send 32 bits to that website, and then the website will send them back. And you're measuring how long in milliseconds it takes. So if you ping Google and you have like 30, it'll say like ping 30 ms, so it takes 30 milliseconds for it to reach Google and come back. Traceroute. This one, if you type Traceroute in the name of a server, it will basically see the path that the packet takes to go from your server or your computer to the server, and it'll take about 10 or so leaps. So if you type like Traceroute and then Google, it will print out the 10 steps that it takes to get from your computer to wherever its in-game is at google.com. It will not show you how many people are using Google right now. If you've seen the video where someone tries to say that you can hack people's IPs using Traceroute, if you haven't, you should watch it. It's pretty funny. I'll just leave it at that. So NetStat's used to display different types of network configuration, connections, routing tables, port values. A lot of things you can do with NetStat. Typically when I run NetStat command, I have about 3 different switches on average. So if you look at these, like this is like a typical NetStat command, netstat-natp. You want numeric values of the active connections that are TCP and their processes. So 4 different switches just to get that specific niche return that you want. So again, man pages are really important for this one, so you can get exactly what you want. Telnet is used to just connect to a server and send data back and forth in plain text. There is no encryption or security at all, so if you're worried about something being insecure, then you won't use Telnet, but it's convenient, and if it's a trusted host, then it's pretty useful. So if you want to learn more about networking in class, there's a few classes you can take. There's also a security presentation that, is, if you look back through our old PowerPoints, there's one that we gave about this time last year, if you want to look through that one. Classes available for this, Computer Read 230, 231, those both go a little bit into how networking works. 489, I'm not too familiar with. There is CompSci 489 for any CompSci, or not 489, but it's high 400 class. That's CompSci for any CompSci majors out there. 530 though, this is probably the one I recommend. It's listed also as 430, and even though it's a 400 level course, from what I've heard of people that take it, it's really not that hard, and the prereqs aren't too enforced. That's a good one to take. And then 541, if you take the first 4, or if you take 3 or so, and you want to keep going, 541's there. It's probably the more advanced networking class. Questions about anything I covered or didn't cover? Nope. All right, that's all I got.